Radulescu from Mount Sinai University, and she'll be talking about attention and affect in RLDM, insights from computational psychiatry.
All right. Hello, everyone. Thank you for having me, and thank you for the opportunity to speak. My name is Angela Radulescu, and I wanted to say before starting this talk that some of the themes in the talk involve mental health. So if at any point those create uncomfortable emotions, feel free to do whatever you need to do to sort of take care of yourself. So with that, I also want to start by acknowledging the people involved in this work, in particular my graduate student, Jing Li, and my graduate student, Christina Mayer, along with collaborators Mark Ho and Ignacio Saez. So I'll start with a little bit of background and motivation. So computational psychiatry is a field of study that applies formal models to understand the precise mechanisms that give rise to symptoms of mental illness. And generally, the goal in the field is a mathematical understanding of latent drivers of behavior that can enable us to design effective mental health interventions. Now, frame disclosure, if you've been at the tutorial earlier this week, the frame is reinforcement learning, but there's different ways that we can think about the mind and the brain in computational psychiatry. But the reason that RL has, I think, been particularly useful in this domain is because we can simulate and fit behavior across different model systems, humans, animals, artificial agents. We can try to infer latent cognitive and affective processes that might drive behavior. And we can identify neural mechanisms and sort of port concepts across different model species and in different types of ways in different tasks. Now, in past work in the field, I've been particularly interested in how attention shapes state representations in reinforcement learning. So the insight from that work was that humans use some kind of attentional process in order to constrain the dimensionality of the stimuli that they learn about. And they have to somehow also learn to direct attention to relevant features of the environment. And we have some evidence that this process is driven by sparse, fast inference about what states of the environment are actually relevant. So this is where I'm coming from to tell you about the work I'll present today. More recently in my lab, we have been interested in bipolar disorder or bipolar spectrum disorders. And rather than define bipolar disorder for you, I'm going to show you these two pictures that were drawn by Sophia Roman, who was diagnosed with bipolar disorder maybe about 12 years ago, and has created art during different phases of her illness in order to document the feelings that came up in those in the course of experiencing those emotions in those states. Now, from a dimensional perspective, some people have proposed this view of bipolar disorders, particularly Angst in 2007, that we can think of the bipolar spectrum as existing on a proportionality spectrum, which includes the presence of depressive symptoms from an extreme of only depressive symptoms and only manic symptoms, and a severity spectrum. And the severity typically in psychiatry means have people presented with sort of psychotic behavior. Okay, so how do we actually sort of make diagnoses along the spectrums of people kind of can exist along the spectrum? Sort of different names for different conditions that have been related to the sort of bipolar spectrum idea. And there's an open question as far as case cutoffs, right? So where do we draw the line on the spectrum in order to diagnose people and improve intervention? This is an open problem. In fact, if you ask psychiatrists to sort of try to differentiate bipolar disorder specifically from other types of diagnoses, this is a poll that was conducted in 2018 with psychiatrists from who were registered on psychiatrist.com, and you find that there are different diagnoses that are especially difficult to sort of differentiate from bipolar disorder. The top one there was borderline personality disorder, followed by unipolar depression, attention deficit hyperactivity disorder, and schizophrenia. In fact, to actually accurately diagnose and treat bipolar disorder, it can take anywhere from 2 to 10 years to do that, and to sort of provide patients with the sort of help that they need. And it's a journey. This picture of diagnosis is sort of complicated by the dynamics of bipolar disorder. So bipolar is by definition a dynamic illness, right? So psychiatrists sometimes talk about this idea of a prodrome. So prodrome refers to the things that happen before an episode, right? So the sort of subthreshold things that sort of don't cross this like window of tolerance and don't result in major episodes, right? And this type of nomenclature applies to bipolar, but also other disorders as well, such as schizophrenia. So in a sense, the sort of question that I'm posing in this work is really what might the prodrome of bipolar look like? How would we know, right, that someone is sort of experiencing this and potentially like about to enter a state in which they can cause themselves harm or cause harm to others, or to sort of make decisions that to us seem inexplicable. Okay. Now, clinical psychologists have been talking about bipolar disorder for some time. There are beautiful theories from Sherry Johnson, and there's a book on bipolar disorder by Goodwin and Jameson that sort of goes into the details of this illness. Typically, bipolar disorder is defined by the presence of mania. Right? So what is mania? Mania refers to a persistent elevation in mood, but it also refers to these kind of puzzling changes in goal-directed behavior, right? So people who report being more manic are more likely to initiate hard-to-attain goals. They show increased energy, pressured speech. They show increased goal pursuit. They show faster action initiation. They have increased risk-taking. They might spend money and so forth. And there are also less emphasized, but equally important changes in social cognition, right? So in particular, people with bipolar disorder, especially in the sort of more extreme sort of parts of the state, can display grandiosity, right? So we have models in the field that have really nicely kind of described or tried to explain sort of persistent mood elevation from the perspective of reinforcement learning from Rutledge and Eldar and Bennett and others. And the idea here is that we can think of mood as a recency weighted average of reward prediction errors. Now, if you sort of do that and kind of invoke a sort of reward sensitivity parameter in a TD learning setting, you end up with sort of with instability that is characteristic of the manic and depressive cycle. To me, however, when I'm reading these papers, one thing that it's difficult to reconcile with this type of model are these other symptoms of sort of goal-directed behavior, in particular, this sort of idea that people with bipolar initiate difficult to achieve goals, and they sort of go out of their way in order to actually attain them, right? And sometimes they don't, and that can be difficult. And these models also, because of the sort of nature of how we've written down RL here, they don't really speak to how and why someone might become like grandiose, right? So in this work, really, it's a project of translation in which we've tried to take ideas from clinical psychology, particularly Sherry Johnson, to kind of formalize these theories in sort of in an RL setting, right? So the behavioral activation system theory of mania that Johnson and colleagues have developed states that one way that this could happen, that mania could happen, is that optimistic overgeneralization can lead to people sort of feeling more activated, right? Which over time, not immediately, but there's a lot that can happen in between, may lead to an increase in manic symptoms. And there's some evidence for this sort of theory, right? So people who self-report more extreme attributions, whether they're positive or negative, are more likely to experience a mood episode a little bit into the future. And extreme self-reported optimistic attributions are also associated with more lifetime episodes of mania. This kind of raises the question, or raised the question to me, and I pose this to the group. How does positive overgeneralization lead to behavioral activation that's characteristic of these manic states? So this is kind of the guiding question of this work. Okay, so we're not starting from scratch. So we have models in the literature based on reinforcement learning of anxiety and pessimism. Specifically, this model from Zorowitz and colleagues has, I think, been really sort of foundational, at least to how I think about these phenomena. So the idea here is that we can sort of let an agent exist in the real world, and we can quantify a belief that the agent has about the probability of taking the best action in the future, right? So you can think of, we termed this, or Sam termed as self-efficacy, and you can think of this as the probability that how much do you think that you're going to be able to actually maximize, like, from the next state, right? And when you write down Bellman equations in this way, and you run dynamic programming and so forth, and sort of you get value functions, what you see is that when you sort of do this kind of weighing of self-efficacy, you end up with behaviors that in the setting look like full maximization, or look like complete avoidance, right? And one of the things here is that, like, you also need a threat, right? So you need like both rewards and threats to sort of make this behavior happen. The idea here that the Sam proposed is that this kind of self-efficacy belief can explain the kinds of like avoidance behaviors that we see in anxiety. So starting from that and sort of thinking about mania as a state in which goal pursuit is dysregulated, we ran simulations of repeated goal pursuit and simple grid worlds, and this is work by my graduate student Jing Li. So we did here, we just sort of wrote down Q learning, right? The value of the action in the current state equals the it's updated in proportion to the prediction error times the learning rate. And the prediction error is has this sort of this property where, like, when you look into the future, you also weigh the probability that you're going to do the best thing by your self-efficacy. And Jing, reading work from Bandura and sort of older psychology theories, like, wondered what would happen if you instantiate Q learning with dynamic self-efficacy beliefs. Right? So dynamic self-efficacy here means that we're letting the agent learn its own belief in the probability that it will do well in the future. Right? And one way to thinking about this just as an intuition is that, like, getting closer to the goal makes me think that I can maximize more in the future. That's sort of the idea, and that's how I'm thinking of W here. And we write down a rule that says the self-efficacy increases as the agent approaches the goal and decreases otherwise. So the first finding here, the sort of insight here was that as agents sort of have more sensitive self-efficacy beliefs, so they update their belief in their ability to maximize in the future faster, they will develop overgeneralized reward expectations, which is exactly what we were like thinking about from the sort of clinical psychology perspective. And interestingly, this sort of makes a series of behavioral predictions, right? So given the same distance, right? We're in a grid world, but let's call it distance from given the same distance from goal, an agent would anticipate more future reward, it would initiate action faster, it would expend more effort to get to the goal. Right? These are sort of pieces of things we can put together from knowing how value impacts reaction time and behavior from the rest of the literature. So next we got curious, okay, so what if you end up with sort of extreme changes in self-efficacy, right? So are there regimes in which like we can reproduce some of the behavior that we see in mania? So we ran the model and you know, when Jing showed me this, I was both excited and sort of terrified at the same time because it felt like we broke RL a little bit. Which I think we might have, but we will fix it in the future. But the point is that as we did this, we realized that there are regimes, so there are sort of regimes in which, like, in a sort of repeated goal pursuit setting, like a more sensitive sense of like self-efficacy will like first like it might make the agent first more distractible, right? So you can see the sort of the value function moves around towards parts of the environment that don't really have to do with the goal. And also, as you push this to the extreme, you end up with these sort of value attractor states, right? In which the agent kind of goes around in circles and really doesn't, it can't exit that part of the space, right? And it's of course very far away from the goal. So this was exciting from a psychiatry perspective to me because it sort of gives us a sort of hypothesis for what a symptom trajectory might look like, right? So if you remember the plot I showed you, we don't know very much about how bipolar disorder sort of changes or evolves over time, but we can sort of use continual reinforcement learning in this case to kind of generate hypotheses about what that might look like. So that's that's a piece of work. But how do we actually test this theory, right? So we saw that the model kind of predicts that positive overgeneralization could be a useful, what we call biomarker, that if we measure, we might be able to sort of prospectively make inferences about the agent sort of going into those kinds of states in the future. So to test that idea, we developed, or rather, Jing developed a task together with Maya and Olivia, a task that measures positive overgeneralization. And we call this the Dino Fossil Hunt task. We tell online participants that their job is to examine newly uncovered fossils and predict whether they're valuable or rare dinosaurs, or they're from more common or less valuable species. And we train people at sort of two extremes of a perceptual continuum. And these are stimuli that were matched in sort of perceptual similarity. So we train people to sort of learn that like one part of the continuum is valuable and one is not, right? And they have to sort of tell us that. And then in the subsequent testing phase, we ask them whether intermediary stimuli, right? So these are dinosaurs that they've never seen before, but that are closer or farther in perceptual space to the extreme dinosaurs, whether those dinosaurs are valuable, right? And we ask, okay, like which one of these stimuli do you think is more valuable? So if people overgeneralize, right, they should consider, like if they overgeneralize and like if reward is overgeneralized, they should consider most stimuli in this set to be valuable, right? And otherwise they would sort of draw this is sort of what we call neutral generalization, right? It would just, the cutoff would be in the sort of exactly in the middle, right? So here is here's a plot that shows you the sort of behavior of a participant in this task. So this is a participant who displays near perfect, like we're sorry, the neutral generalization. And this is a behavior of a participant who displays positive overgeneralization. So here on the x-axis, you see the percentage of time that the participant said that the dinosaur was valuable versus not. And we can see that this sort of curve like shifts around, right? So this gives us a metric for the extent to which people generalize. Okay, so what can we do with that? So we can take this task and essentially measure individual differences in the tendency to overgeneralize. And we can correlate that tendency with different self-report measures of individual differences. And I won't take you through all the questionnaires that we used. We sort of selected the questionnaires as questionnaires that have been sort of considered relevant for bipolar disorder, and we also use questionnaires that have actually been developed to measure positive overgeneralization in real life. I'll just show you what we find. So, here are the results from that. So here on the x-axis is the correlation between the task-based measure of overgeneralization that we developed and scores on these different questionnaires. And to give you an example, so let's see, we have let's see, self-reported period. Okay, so there's this construct of self-reported upward positive overgeneralization. So people are asked to rate how much they believe sentences like this one. When one thing goes right, it makes me feel that my possibilities are limitless, right? Or something like reward responsiveness would say, it would excite me to win a contest, right? So these are the types of questions that we ask people. And essentially what we found is that as we expected from this model, and is sort of consistent with these BAS models, which was encouraging to us, is that lifetime self-reported bipolar traits at the subclinical level, right? So we can measure these things continuously in the population, but at the subclinical level, you get a continuous measure. Those are indeed correlated with task-based overgeneralization. And we also encouragingly found some external validity for this in the sense that the self-reported positive overgeneralization is correlated with the measure in our task. The more surprising finding was the sort of behavioral inhibition finding here. We weren't really expecting to find that based on like previous accounts of sort of mood being affect, what we call affect congruent. So here, affect congruency refers to the fact that if we train someone to think about positive things, they should sort of pay attention to positive things, and that's sort of not what's it's not really consistent with this. But to sort of sum up these results, we find that people who are more likely to endorse statements like, when one thing goes right, it makes me feel that my possibilities are limitless, and who are more likely to report clinical lifetime BD traits are also more likely to overgeneralize in the behavioral task that I showed you. Okay, I think I've already said all that. Okay, so in ongoing work, we're sort of trying to put RL back together as it goes, because we realize that we need a better definition of self-efficacy. Right? So in order to sort of explain some of these phenomena, we need some understanding of how the belief in one's sort of ability to achieve what they want to achieve gets updated in a reward setting. And if you're in an RL setting, if you're interested in that, stop by Jing's poster today. This is a project in collaboration with Mark Ho. Okay, so switching gears a little bit, what about the brain? And what can we do with all of this? What is the point of sort of designing these tasks and like kind of, carefully kind of constructing tasks that can tell us something about a construct like generalization? Well, one reason is that if we do that, then we can also look in the brain for signals that might be sort of usefully leveraged for example, for treatment purposes or for monitoring purposes. So in this project, Christina Mayer has been doing really amazing work, essentially running reinforcement learning tasks in an interoperative hospital setting. So these are patients who come in to get sort of treatment for epilepsy. They have electrodes implanted in their brain, and they dedicate some of their time and energy to play the computer games, the tasks that we've designed for them. And in this project, Christina developed a gamified version of a multidimensional bandit task, in which people were asked to select the best out of 3 stimuli, where the stimuli varied along 2 dimensions, shape and color. So we ask people to select the best gems. And again, we have to gamify this because especially when they're sort of sitting there and playing tasks and stuff like people like fun games more than they like psychology tasks, right? So we did Christina did a lot of work to gamify this in a way that was helpful for participants and is easy for participants to learn. And then once we have that, we can sort of deploy the techniques that have been developed in computational cognitive science for fitting individual differences parameters to people's behavior to understand how cognitive processes, for instance, selective attention, impact behavior in the task. So in this particular case, we developed a model that quantifies the extent to which people pay attention in a focused manner to only one dimension of a stimulus, or more broadly to both dimensions of a stimulus. And we can kind of infer from participants' behavior whether they were sort of tend to attend more broadly or more narrowly to stimuli as they learn. And you can here, at least you can think of attention as kind of implementing a sort of mechanism for generalization, right? So as you attend more narrowly, you're going to kind of under generalize. So as if you attend more broadly, then you might overgeneralize. You might attribute reward to several features in the environment. So with that approach in hand, and with and leveraging recordings from the human LPFC and the human OFC, we asked what are the neural mechanisms that might support this kind of attentional sort of control of attention during learning. I'm happy to tell you about why we picked these particular regions, but I think we'll leave that for offline. So it's recorded from LPFC and OFC. And we found that the connectivity between these 2 regions depends on the value of the stimulus on each trial. And we further found that depending on sort of where people are in the learning process, depending on whether they're, or we look at this connectivity on trials where in which the option that they chose has a high expected value, or in trials in which the options that they chose has low expected value, that has bearing on sort of crosstalk between the 2 regions, right? So we see in particular that on high expected value trials, before the participants choose, this region in the brain called lateral, like LPFC, leads or shares information with the OFC, which is what you would expect from the perspective of cognitive neuroscience. LPFC has been involved in the sort of top-down control of attention. While on low expected value trials, the LPFC leads the OFC after outcome, right? Suggesting a more sort of learning-driven process, suggesting that attention or attentional control comes online as participants are trying to learn from the outcome. And if you're interested in this work and haven't attended Christina's great talk yesterday, we have a paper in the iClear Realign workshop that you can check out. Okay, and so going back to individual differences, so we can also ask what is the extent to which attentional strategies that people use throughout the task shape the sort of temporal dynamics profile between of information sharing between these two regions. And we found that the way in which these two brain regions talk to one another depends on whether a participant was sort of classified as like having high, like sort of using high selective attention or low selective attention, right? So the participants who tended to attend more narrowly showed the behavior that showed the profile on the left, while the participants who tended to attend more broadly showed the profile on the right. Okay, so just in summary, told you about reinforcement learning with dynamic self-efficacy as a potential model of mania. This model suggests that positive overgeneralization is a useful perspective biomarker that we can sort of measure and try to potentially intervene on. We have developed a task-based measure of positive overgeneralization that shows some external validity to self-reported overgeneralization, and we're in the process of replicating that. We've shown that this positive overgeneralization measured in this way is related to lifetime self-reported symptoms of bipolar disorder. And I've shown you results suggesting that the coordination between the lateral prefrontal cortex and the orbitofrontal prefrontal cortex might be a useful potential neural mechanism for attention and generalization. And with that, thank you all for listening, and thank you to my amazing lab, everyone at the center at the Mount Sinai Center for Computational Psychiatry, and all my mentors and collaborators, some of whom are somewhere around.